This is 3.2, day 2, and 3.3, day 1. We'll first focus on graphing logarithms, and then get into the properties. Okay. First slide is I want to just review how you graph an exponential function. So we're going to graph the red function first. Y equals 4 to the x power. So let's substitute 0 into the function. So if I substitute 0 into the function, what would I get? 4 to the 0 power is 1. And I substitute 1 into the function. 4 to the 1 power is 4. Substitute 2 in. 4 to the second power is 16. If I go backwards, negative 1. 4 to the negative 1 power is 1 over 4 to the 1, which is 1/4. Okay, so let's just take those ordered pairs and graph the exponential equation for y equals 4 to the x. So I'll graph my critical point first. Over 0, up 1. And then over 1, up 4. And then negative 1, up 1/4. So this is kind of a review from a couple days ago. Now, here's how you graph a logarithm that has that same base 4. What you do is you just interchange all of the ordered pairs, because a logarithm of base 4 and an exponential base 4 are inverses of each other, and they're reflected about the line y equals x. So I'm going to take those ordered pairs and flip-flop them. So now this ordered pair is going to be 1, 0. That ordered pair is going to be 4, 1. This ordered pair is going to be 16, 2. And then 1/4, negative 1. And that's for graphing a logarithm of base 4. So now let's just see what the difference is when we graph it on the same coordinate plane. I'll give you a minute to kind of catch up with your writing those down. So I'm going to graph the critical point. The critical point is the same as 0, 1, but flip-flop now it is 1, 0. So my critical point is now an x-intercept. The next point I'll graph is, instead of being 1, 4, it's going to be 4, 1. And then 16, 2 is off my graph. So now let's just do 1/4. So very, very close to that vertical axis, and then down 1. All right, that is the logarithm of base 4. I am going to just graph that line of symmetry. That line of symmetry is at y equals x. It has a y-intercept of 0 and a slope of 1. If I imagine folding my piece of paper along that imaginary green line, the two curves would be smack dab on top of each other. So let's talk about the domain of the red one. What's the domain of the red one? What type of numbers can I plug in for x? All reals. We learned about that when we graphed a couple days ago. That exponential functions have the domain restriction of nothing. What is the range? What type of numbers am I getting out?
Greater than 0.
Yep, y greater than 0. Where is my y-intercept at? Over 0, up 1. increasing, and it has an asymptote where?
X equals
Y equals 0. Now let's talk about the important pieces to the blue one, the logarithm of base 4. What's the domain there? What type of numbers can I plug in for x? Or look at my graph. Where is that blue function happening at?
greater than 0.
Greater than 0. So when we think back to yesterday's lesson, I asked you to evaluate a function for a logarithm which had a negative in it. And I said, don't worry about it. We'll talk more about it tomorrow. Whenever we got an error or error domain or a non-real number, that's what is true about it. For a logarithm, any base, you cannot substitute evaluate the function for a negative. It does not exist. So it has a domain restriction. It has to be greater than 0. What about the range? All reals. What about the y-intercept? Is there a y-intercept? No, but what is there instead? An x-intercept of 1, 0. So that would be my critical point. Well, if we had our critical points for the red functions, exponentials at over 0, up 1. And then where would be my asymptote now? Very good. So I would have a vertical asymptote right there at x equals 0.
So everything just like flip.
Everything just flip-flops. Yeah, they're inverses of each other. So every ordered pair, and if we think back to some chapters ago, that's what we talked about with inverse functions. You just flip-flop those ordered pairs, and they'll be symmetric about that line y equals x. We proved it by doing composite functions, f of g of x and g of f of x, and both those values have to equal x. Okay, so let's now talk about this function. Think back to those important transformations that when we were introducing all those parent functions. And then on my whiteboard off to the right of my room had all those important pieces to the transformations, and I required you to memorize them. Yep, they're coming back into play again. What would the minus 4 inside the function do? Moves it 4 to the right. So now that I know like the parent function of y equals log base 4 of x, I could graph that function like I did on the previous slide, and then just shift everything right 4 units. And usually like 2 points is probably enough. So if I graph this ordered pair again, 1, 0, and 4, 1, I would just pick up those 2 pieces, 1, 0, and 4, 1, and shift those 2 points to the right 4 units. So now in the red, this point would be at, 5, 1, 5, 0. And now my asymptote has changed places. Where is now the asymptote at? X equals 4. So that's how transformations help us. I'm going to stop the recording there.